oxidation states and the balancing of redox reaction. So we are trying to look at how to go about balancing redox reactions. But before we talk about redox reactions, balancing of redox reaction, we'll look at the oxidation states of metals. Now, oxidation states of elements must be known so that it can help us to balance redox reactions. And we shall get to see that. Now, when we talk about oxidation states or oxidation number, the oxidation number of an element is in its uncombined state generally is 0. So if we are talking about assigning oxidation number of any element that is just on its own is 0. Any element on its own that is not combined with another element or other elements, its oxidation number is 0. The oxidation number of group 1 metals or group 1 elements, not just metals, because hydrogen is in group 1 and it's not a metal. So the oxidation number of group 1 elements is +1. Group 2 elements, yes, is +2, and group 3 elements also is +3. The oxidation number of hydrogen generally is +1, except when it is in the hydride compound, like sodium hydride, potassium hydride, calcium hydride, like that. So when it is in its hydride state, it has an oxidation number of -1. That is for hydrogen. When it is in the hydride state, it has oxidation number of -1. But apart from hydride states, the oxidation number of hydrogen is always +1. The next we have to take note of is the oxidation number of oxygen. The oxidation number of oxygen is always -2, except when it is in the peroxide compound. In peroxides, the oxidation number of oxygen is -1. The next oxidation number we need to take note of is oxidation number of halogens. Oxidation number of halogens is normally -1. But there are halogens that are peculiar. Fluorine has oxidation number of -1 permanently. Astatine has oxidation number of -1 and +1. That is to say, it exists in these two states. But the other halogens, especially chlorine, bromine, and iodine, also show oxidation states of +1, +3, +5, and +7, excluding the normal -1 that the halogens are known for. So these other halogens show +1, +3, +5, and +7 oxidation states. And this is when they are seen in their compounds like the oxoacids and the oxide forms. So in their oxides and oxoacids, they are seen to exhibit oxidation states of either +1 or +3 or +5 or even +7, depending on the compound in question. So this is what we should know. Lastly, talking about oxidation states of elements, if we are to calculate the oxidation state of an element that is in a compound, we have to first of all understand that the summation of the oxidation numbers of the elements in a given compound is equals to 0. But if it is a radical, that is to say an ionic representation, then it will be equal to the ion, the charge of that radical. That is what we are trying to say. The sum of all oxidation numbers of elements in a compound is 0, but in the ionic state, it is equal to the charge of that ion. We shall get to understand this when we carry out some calculations. So let's look at sodium, for example, sodium chloride. Looking at what we have on the screen, we can see that sodium chloride as a salt, when it dissociates in water, it will dissociate to giving us sodium ion and chloride ion. It will dissociate to give us sodium ion and chloride ion. Now, the sodium ion and chloride ion will be expressed in terms of oxidation and reduction. So let's look at sodium chloride going to sodium ion and chloride ion. So we said that the oxidation state of a compound equals 0. Why? Because look at sodium, for example, is +1. Chloride is -1. +1 and -1 is 0. So, but when they dissociate in water, sodium will become +1, chloride ion will be -1. So you can say this is an example of oxidation reduction. Look at sodium has gone, this is 0, this is 0. So generally the compound form is 0 because +1 and -1 will give 0. So the compound form of this is 0. Now, but when it goes into water, sodium has gone to from 0 to +1 because they dissociate as ions. But looking at the chloride ion has gone from 0 to -1. So we can see that sodium went from 0 to +1, but chloride ion has gone from 0 to -1. 0 to -1 is reduction, but from 0 to +1 is oxidation. So it tells us that this is an example of an oxidation reduction reaction. Oxidation takes place here, reduction takes place here. When we talk about something going from 0 to minus, tells us that it's reduction because mathematically the number line has to do with 0 at the middle. Here we have 1, 2, 3, 4, 5, etc. And at the left hand side we have -1, -2, -3, -4, -5, etc. So when a value goes right, it tells us that it's increasing, positive side. But when it goes left, it is decreasing, negative side. So -1, -2, -3, -4, -5 are all less than 0. But anything from 1, 2, 3, 4, 5 are greater than 0. So when a number goes from 0 to -1, it means that it has reduced. But when a number goes from 0 to +1 or +2, +3, it means it has increased. So that is actually why we say that the chloride ion going from 0, which it was in the compound state, here to -1 is reduction. But sodium ion going from 0 to +1 is oxidation. So that is actually what we should understand. So when sodium goes from the metallic state, because we said that the oxidation number of a metal alone is just 0. And that is actually what we are looking at here. So sodium in the metallic state is 0. Chloride ion in its normal elemental state is also 0. So if it goes to the -1 state, it is reduction. Sodium going to the +1 state is oxidation. So this is just a simple explanation of how oxidation reduction reaction takes place. We now proceed to looking at how to calculate oxidation numbers.